So now let's look at a 3-pole amplifier. And so you might be asking yourself, why do we keep adding a pole to each of these? Why do we want to consider a 3-pole amplifier? Well, a 3-pole amplifier is particularly relevant because this is a good model for an op-amp circuit. So we haven't talked about sort of the inside workings of our op-amp, but if you want more details on that, you can look at various chapters in the textbook, particularly chapters 12 and 13. And so what you would see as you look in those chapters is that our op-amp can be represented by this simple block diagram here. We have our two inputs V1 and V2, which go into a difference amplifier, so that's sort of our input stage. We then have a gain stage where we're amplifying the difference, and then finally we have an output stage, which ultimately gives our output voltage V out. Each of these stages is going to have an associated input resistance and some type of capacitance, which means each one is going to introduce a pole. So we're going to have 3 poles. So we can then express our open loop gain of the system. So our open loop gain can be given as A is equal to, and we're going to have 3 pole terms in the denominator now. And in the numerator, we're still just going to have this low frequency gain term, A naught. So we're going to have our first pole is 1 plus J times omega over omega 1. We're going to have a second pole, 1 plus J times omega over omega 2. And then finally, we'll have a third pole, which is 1 plus J times omega over omega 3, where each of these 3 omega values are omega 1, omega 2, and omega 3 are unique corner frequencies. So like I mentioned just a second ago, this value up here in the numerator, this A naught, is again our low frequency gain. And we're going to make a similar assumption as we have with our 2-pole amplifier. We're going to say, let's assume that these poles are really far apart. In other words, we're assuming that our omega 3 is much greater than omega 2, which is much greater than omega 1. And so again, another way to say that is just to say that our poles are far apart. And that's just going to make our initial sort of approach at this with our Bode diagrams a lot easier to sort of draw. So speaking of Bode diagrams, let's draw those, keeping in mind this assumption about our frequencies. So I've already actually got some plots here ready. So for our gain, we have our key frequencies marked. Our corner frequency is omega 1, omega 2, and omega 3. And then for our phase plot, we see we also have 1 decade above and 1 decade below each of those 3 corner frequencies. Because we've said they're far apart, notice we don't have any sort of overlap. So our 10 omega 1 is less than our 0.1 omega 2. Same way our 10 omega 2 is less than our 0.1 omega 3. And so that's the reason we make that assumption about the poles being very far apart. It makes that plotting a little easier. Okay, so let's start by looking at this gain plot. So we have our low frequency plot is just going to be a constant value at this 20 log of our low frequency, because again, it's in decibels, until we get to our first corner frequency, omega 1. After we get to omega 1, we're going to be decreasing at a rate of negative 20 dB per decade. And let me actually make this a little shallower because I've drawn my poles kind of far apart. So let's say we're decreasing at a rate of negative 20 dB per decade after we get to omega 1. Now, at some point, once we get to omega 2, we have sort of our second pole kicking in. So maybe let's do it this way. It's going to be easiest. So after we reach omega 2, we have our second pole, which means we're now going to be decreasing at a rate of negative 40 dB per decade. So I know that's maybe not very clear to see in my drawing. Of course, you can look in the textbook to see sort of a more clear representation where the slopes are easier to differentiate. Once we reach our third quarter frequency, we have an additional contribution of negative 20 dB per decade, so that our overall slope in this region is going to be negative 60 decibels per decade. And that just continues as our frequency continues to increase. So we see once we get above that omega 3, our magnitude is dropping a lot quicker. So moving on to our phase then, we're going to use that information. We know that for one pole at omega 1, our first quarter frequency, we're going to have a negative 45 degrees. We're saying for our linear approximation, let's say once it gets about 10 times greater than that omega 1, we're at negative 90 degrees, and 10 times less, we're just at 0. So we have something that looks like this, and we just connect that with a linear line. And so I've drawn that sort of poorly, but that should be a linear line connecting those. And so of course the slope is negative 45 degrees per decade. So now negative 90 sort of becomes our new baseline as we do that same process with omega 2. So we decrease by 45 as we reach omega 2. Less than a tenth of omega 2, we're still at that baseline value. And then if we get above 10 omega 2, we're constant at negative 90 below that baseline. And again, in this case, our baseline would be the negative 90 degrees. So negative 90 minus 90 puts us at a final value of negative 180 after pole 2. Same idea with our pole 3, except now our baseline is the negative 180. So we're negative 45 degrees below that baseline at omega 3, negative 90 degrees below at our 10 times omega 3, and we are at the baseline until we get to a tenth of omega 3. And the connection between them is linear, so we get something that looks like this. So of course with this 3-pole system, now we can see it's very probable that we can have this phase angle of negative 180 degrees, and we also have our magnitude decreasing. So what we're going to do in the following videos is come back and look at how we can use a couple different methods to determine the stability based on these types of plots. But one thing I just want to reiterate, which I've said in a previous video, is ultimately we set out to investigate our loop gain. So remember, we wanted to investigate our loop gain, T of S, or we also called it T of j omega, and we wanted to look at its frequency response because we said based on the magnitude and phase of this loop gain, we can tell if we're stable or we're unstable. But we've been looking at these open loop gain equations of A of S or A of j omega. Well, remember that our T of j omega is just beta times our A of j omega, where beta in this case, our feedback transfer function, is just going to be a constant. So all we have to do for each of these 3 scenarios are 1, 2, and 3 pole systems. We just multiply this by our beta. So we would come in here and multiply by beta to get our T. So this would just be multiplying by beta in here. So in general, keep in mind, as we've seen in all of our Bode plots then, that our frequency response, or rather our loop gain response, is a function of frequency. Both the magnitude and the phase of our loop gain are going to depend on frequency.